Consider the two-dimensional region bounded by y equals square root of 4 minus x squared and y equals quantity x minus 1 squared. And suppose f of xy is some function defined in that region. Our problem is to set up double integrals of f of xy over this region, one with f of xy dy dx and the other with f of xy dx dy. First, realize that y equals square root of 4 minus x squared is a semicircle of radius 2. It is equivalent to x squared plus y squared equals 4 with y non-negative. In addition, y equals quantity x minus 1 squared is a parabola with vertex at 1, 0. The graphs of these functions look like this. The region bounded by these two curves is shaded here. This region can be described by the following set. And the integral can be represented this way. It would be easiest to set up the integral by choosing x first, so we would like to know the x-coordinates of points A and B. We can find those x-coordinates by solving the two equations for the two curves for the common x. And we have these values for A and B. So if we choose x first, then our outer integral will have limits of integration from x equals a to x equals b. And we have this much so far. Having chosen x, we must now choose y, and this choice depends on our choice for x. We are going to add little rectangles of height dy on the dx strip. We must choose y between y1 and y2. These are the y values on the parabola and circle, so y1 is quantity x minus 1 squared and y2 is square root of 4 minus x squared. And now our integral would look like this. Now let us consider choosing y first. We will need the y-coordinates of points A and B, and those can be found by substituting the x-coordinates into the equation of either curve. These y-coordinates are as shown here, and for simplicity, however, we'll just call them C and D. If y is above C, then the minimum and maximum values of x are determined by the circle, the red curve. So we would have x between negative the square root of 4 minus y squared and positive the square root of 4 minus y squared. On the other hand, if y is between c and d, then the minimum value of x is determined by the parabola, the blue curve, and the maximum by the circle, the red curve. In this case, x would be between 1 minus square root of y and square root of 4 minus y squared. And finally, if y is below d, then the minimum and maximum values of x are determined entirely by the parabola, the blue curve. And in this case, we would have x between 1 minus square root of y and 1 plus square root of y. Putting this all together, we can now write as the sum of three double integrals like this. In this problem, choosing x first led to a much simpler setup. This was because the boundaries could be represented as functions of x. In situations where at least one of the boundaries cannot be represented as a function of x or a function of y, it may be necessary to split the region into several regions and add the corresponding integrals. For example, the following region would have to be split into two regions, whether x is chosen first or y is chosen first.